Welcome to this third session of Hands-on Deep Learning with MatConvNet. In this third session we're gonna see a couple of tricks to do proper training. So the idea is to improve the convergence of the different methods and to do training more efficiently. To this end we're gonna see how to do proper initialization and the importance of initialization itself. We're gonna see how to apply dropout in order to also enhance the generalization capabilities of our networks, how batch normalization can be used also to improve convergence to better solutions in less number of iterations, which is a very popular technique right now. To start with, we will be using MNIST and CIFAR10 as before in previous sessions, but this time we're going to use reduced version of this dataset. So the same thing, but like with less images, so we can run more epochs in less time and see and compare different configurations, so to understand which things are working better. Okay, so we're assuming you already have downloaded the materials for session 3. That's quite important. In order to start, we need to do some modification to the MatConvNet code. So these modifications are quite straightforward. We only need to take batch norm.m and CNN train dag.m located at the folder session 03. Okay, it will be like this one and this one, and we have to copy them to some specific positions of the MatConvNet folder. So we need to copy batch normalization.m here. Yeah, we want to replace it. And we have to copy the CNN train DAG here. Yeah. Probably in your case it will not ask about replacing, but it's fine. Okay, so far so good. The changes in the code of batch normalization are just to do a better initialization of the layer, just indicating the number of channels. So this is a modification I did to improve the initialization of this layer, but this is not so relevant now. So after we have done this, we can start working on the initialization. So the initialization of a network is quite critical for achieving good results during the training process. So this influences the convergence of the network, so the speed, the convergence, so the convergence speed of the net during training, and also it imposes some limits on the depth of networks you can train successfully. So in general, the idea is that you want your data to flow within some boundaries. So the magnitude of your signal, in this case your images, has to be within some boundaries, so not too high, not too low during the whole process. So as long as the data is crossing across the different layers within these boundaries, the process is going to behave well. And the same is true for the backward propagation, so for the gradients. So your gradients also need to be within certain bounds, not too high, not too low. And usually so when talking about the filters themselves, in order to achieve this bounded magnitude of the data, we need the filter to have some specific magnitudes. So they also have to be like not too high, not too low. So to achieve this, there are some already specific formulas that have been there in the community during for a couple of years already, like global initialization or hash initialization, which is more recent, and so on. But the idea is quite simple. The idea is like you need to initialize your filters so that they make your data to behave properly. So when the data is going through your net. So different layers are going to be initialized in different ways depending on their position within the network and also in their fan in and fan out. So how many neurons they receive and how many neurons they produced. So their connection with previous and posterior layers. It's also important, although this is not typically mentioned, like the magnitude of the original signal. So the values of your input images. So since we can use different normalizations here, like we can have unitary images or we can have images that range between 0 and 180 or 255 or minus 180 to 180 or whatever combination you can think of. So it's very important to also take that into account in order to do the initialization of the filters, because roughly filters need to be, at least the ones that are in contact with the data, they need to be sort of proportional. Their magnitude needs to be proportional to the input data. So perhaps smaller with less magnitude than the input data, but still we need to take that into account. Okay, so in order to understand this a little bit better, we're gonna use Lenet train here, but first we're gonna load the data. Okay, here you see you have already load IMDb, CFR 10, reduce, MNIS, reduce. Okay, it's perfect. And now we are going to start using Lenet train. So we have several options for initialization. So 3 options here. What we're going to do, we're going to be uncommenting one at a time, comparing them to see what's going on. But before that, I would like to comment about initialization, some basic initialization aspects. So let's have a look to initnet. Initnet is this function here. Okay, it's pretty basic. So what this doing is just going through all the layers of the network, checking if it's a convolution layer. Okay, and then we retrieve the indices for the filters and the biases of that layer. So just to see where all the values are actually stored. So we retrieve those values that are going to be initialized to whatever thing, and now we change the initialization of these guys using a random distribution. So we use a Gaussian for initialization, and we are changing the covariance of that Gaussian. So we are scaling the Gaussian with Fi. In this case, Fi is going to be indicated or provided by the user, and we have a different Fi for each of the layers, and the same is true for the biases. So this could be 0 or any other constant, but the important thing here is that we are initializing everything following a random distribution, Gaussian distribution. So why are we not using something like a constant value all across the layers, something like 0 or any other constant? Well, the reason is that if we do that, we will have symmetry all around our networks. So the kernels will be initialized to the same values, and then when we apply back propagation and the update caused by back propagation, all the kernels will be moving the same direction and with the same magnitude. So all of them will be doing the same task. So we will end up with a lot of redundant information, which will be completely useless. So it's very important to break symmetry. That's why we initialize each of the kernels following a random distribution. Okay. So now, after this explanation, let's now comment this line here and run first experiment. Okay, have started training. You see, since I have read it's quite fast to time. So you can see that the objective is not like going down 29, 2.294. Yeah, so it's moving, but it's not moving that much. And the same is true for the objective error for validation, and also for the classification errors across. We're gonna let this running operations. And then I will show you the result of this training. Okay. So the process has finished. So it has run for 60 epochs, and we see that, well, the error was converging, so the objective function was converging, but we stopped it prematurely, just because we want to do some comparison between different methods in a reasonable time. But in general, we can observe that for our classification error here at the left, the training went down to almost 40% of error, while the validation just made it to the like 60 or 60%, a little bit less than 60% of error. So still quite high. Okay, this is what we got with this sort of initialization by using random Gaussians. This initialization we just used is the one is the original one from AlexNet. So basically initializing all the layers by Gaussian with a fixed factor. Okay. The factors we used are here. So basically we initialized all the filters to 1/100. Okay, that's gonna be like the scale of the covariance. And for the biases, we initialize them, all of them, to zeros. So this is a vector of 4 elements, because we only have 4 convolutions, 1, 2, 3, and 4, so the classifier is also convolution, remember that. And with this, the results are the ones we just showed. But now let's gonna see what happened when we change this basic initialization by something more complex. So let's gonna comment this line and uncomment this line. It's gonna be experiment 2 using hash initialization. Let me keep this plot as a reference. Okay, we have started. I'm gonna start the video. Wait a little bit until we are about to reach the 60. And the validation error for is already like in less than. This is showing you that a proper initialization can improve a lot the classification error you get. So we're about to finish. We're about to reach the classification error went all the way down to 0%. Okay, and the validation error went to 30%, which is already a large improvement in comparison with the this one, which was like around 60%. The same is true for the objective loss for both train and validation. So yeah, this is the first proof or the first demonstration that proper initialization can change things a lot. So in this case, hash initialization is a bit more sophisticated than the initialization we saw before. It's still using Gaussian distribution, but then each Gaussian is rescaled following a simple rule that takes into account the fanning of the network, fanning of that layer. So the fanning again is like how many neurons are connected to the input of this layer. The formula is quite simple. Is the square root of 2 over like the fanning, which is basically the width of your kernel times the height of the kernel times the number of input features. Okay. Sometimes we need to adjust this a little bit by a small constant, by multiplying it by a small constant, like in this case we multiply by 0.3. Yeah, these functions are approximations of other proper functions that are more complex. So sometimes we need to rescale them or adjust them a little bit. I would like you to play with these factors to see if you can actually improve by changing them. Okay. Usually that's the case. So you play a little bit with these factors and you end up like earning a couple of extra points. But in any case, the general concept here, it's simple. It's still the same. It's just a way to make the covariance of your data to be unitary. Um, the only thing is that this is a formal way of achieving that by having into account like how many neurons are connected to the input of your network. Okay, we're gonna see the same concept but implemented in a slightly different way. That's called Glorot formula or Xavier's formula, because it was proposed by Xavier Glorot and Bengio. It's pretty much the same concept as Hess formula. So again, trying to have like unitary covariance in your data. But it was proposed for those networks using sigmoid activations and hyperbolic tangent activations, while Hess formula was proposed specifically for ReLU's network. In any case, although we are using ReLU networks, Xavier's formula is working really well. So people use it all around, no matter if they are using ReLU's network or hyperbolic tangent networks. Doesn't matter. So the formula is very similar, but instead of taking into account the fan in of the network, it takes into account the fan out of the network. So how was the size of our output? And in order to do that, we multiply the width of our filter by the height of the filter by the number of output channels, and we do 2 over that square root of that. And again, we have to adjust it by some scalar factor. In any case, so you can learn more about the theory behind this, like following the links and in the website. And I think this is one of the most attractive topics you can learn about, because it really can change everything. It changes how the network is gonna converge. It changes the final classification errors you get. So it's really important to learn about these things. Okay, let's gonna try what happens when you initialize with Xavier's method. And again, let's try to have these guys as a reference. You can see here the objective loss did something quite funny at the beginning, the epoch 2, so it went up a little bit. This might happen sometimes. You don't need to worry about if you see that after a couple of epochs it starts decreasing, so that's fine. But of course it will be better to avoid that behavior. You see that the validation error has already reached 40%. We're gonna wait for couple of iterations until we reach the 60 epochs. So you're gonna speed up. Okay, this is how to finish. In this case, Xavier's initialization didn't reach like a good optimum. So hash initialization gave us like 30% of error in validation, while service initialization is giving us like 40%. But this is still quite better than the 60% of error we got at the beginning. Yeah, sometimes using service initialization might give you better result than hash, and sometimes the opposite can happen. It's just about like trying both and see what's going on. Try to adjust them a little bit, like modifying the factor a little bit and see which one is working better for the specific problem. But in theory, hash initialization should be like the most appropriate for ReLUs, those networks based in ReLU nonlinearity. So yeah, this sort of confirm the theoretical fact. In any case, again, the point I want to make is that different initialization, different ways of initializing your convolutions might take you to quite different optimum, make things to converge much faster or slower. So initialization is very critical, and you should be reading papers about this and getting to know as much as you can about different ways of initializing this network, because there are many ways to do this. So there have been an explosion of paper, like a boom of papers and articles telling you how you should be initializing things, why to do this, why not doing that. Yeah, all of them are very interesting. So yeah, okay, this concludes the part of oriented to initializing the network. Now we're gonna see how to improve the generalization capabilities and avoid overfitting through dropout.